Okay, hello everyone. So welcome back to the course of Introduction to Algorithms. This is week 5. Today's topic is about trees, heaps, priority queues, tries. Actually, this is a continue of the previous week's lecture where we talk about the trees, where we talk about the heaps, and on today's part, we'll talk about the priority queues and tries. So let's get started. So in the previous week we covered what is a tree, what is a binary tree. Uh, if you remember, the binary tree is a tree that where each node has up to two children, so it has no more than two children. It can be 0, it can be 1, or it can be 2. Um, Tree, if you remember, it's a non-linear data structure where to each node it can be a connection to different nodes, so each element can be connected to many elements at the same time. Uh, and In order to visit the tree, you can have different kind of uh, traversals. And when we have binary tree, we have three type of the traversals. First one is in order, second pair, and third one is a post order. So in order is a traversal where you first start to visit everything that is on the left, then you visit the current node, then you visit the right, everything that is on the right side. Meanwhile, in the pre-order, you start with the current node, then go to the left, and then go to the right. Post order, it's you start with the left side, then go to the right, then you visit the current node. So the the ordering in these three traversals as like every time you go from the left to the right, but the only difference is that when do you visit the current node. In order, but you can figure out by through the name. It means that in between, it's between left and right. Pre means before. It means it's before you visit current node before left and right, and post means that you visit after. So it's after visiting left and right side. Binary search tree is a tree where each element on the left, the value of each element on the left is less than the current nodes or equal. Uh, on on the right side, every element is bigger than our current element. So in the binary search tree, the elements has some kind of orderings according to the rule where left less or equal to the current and the right is bigger than the current. So I have already talked about tree traversals. One more very important topic is a complete binary tree. Complete binary tree is a tree where each level is filled from left. So each level has two children except the last one. On the last one, you can have children. The last level is filled from the left to the right side. And the last one was about the binary heaps. It's very convenient data structure where you can get the maximum or minimum at the constant time. So when you have some problem, when you need to operate a lot with the minimum or with the maximum, the min heap or max heap is the best one. So what is a min heap? Min heap is a data structure where the parent is less than its children. So it applies to the whole tree and it applies to the whole subtree. Uh, it's a almost same rule for the max heap, with the only difference where parent or root has the highest value, higher values than its children, and the same applies to its. So all the this rule applies to the whole tree. This rule applies to the whole subtrees, and from that you can assume that on the top of the min heap we always have the mean value. on the top of max heap, we have the maximum value. So this is a topic that we covered last week. So first of all, let me start with the problem. It's a problem related to the previous weeks. You need to work with the binary heap, and you need to put the binary heap into array. So given binary heap, put all the values of binary heap into array so that we can have the same time complexity as we have with the binary heap. So if you remember, one of the biggest advantages of the binary heap, if it is min heap, you can always on a constant time retrieve the minimum value. If it is max heap, you can always retrieve the maximum value on constant time. So you need to create some kind of array where you can always figure out what is the minimum element, and one you can always figure out what is the parent of the nodes. So let's say we have this kind of max heap, as you can see, because the value of the parent is bigger than the value of its children, and it applies to this subtree, and also the whole tree itself. So so what I want to say is that binary heap, if you remember, is a complete binary tree. It means that every level is filled with the nodes with the elements, except the last one where the elements are filled from the left to the right side. So that's why we don't need to worry about the null values between the elements. So guys, this is a problem. So before going to the solution, you can take a pause. You can think how to approach this problem, how to tackle this problem. Think about this like couple minutes or 3 minutes, and then try to compare your solution with the solution which is on the lecture. So in order to solve this problem, let's say that we have this kind of min heap. So on the min heap, the parents are the values of the parents are less than its children. So we can take the ordering of all elements from the binary heap. For example, the root is always the first element, and the left child is the second, right child is the third one, and so on. So if we put binary heap into the array, we would get this kind of array. And as you can see, the first element is a root, and we can always retrieve the element on a constant time. But the problem is that, let's say that we want to remove some element. Let's say it's 5. So when we remove the 5, we need to rebuild the whole tree, and we need to know what is the parent of the 5, and we need to know what is the children of the 5 by just looking at this array. And after looking at this array, we need to replace the 5 with its children. But how to do that? We can follow this rule where, for example, let's say that we want to know what is the parent of the 5. In order to know what is the parent node, we use this formula. So I is this index, which is 3. So we subtract 3 from the 3, 1, and then we divide, so it's a 1. So the parent of the 5 is an element on the first position, so we can always say that. And we need to know what is the left child, and we need to know what is the right child. And we take this 3, put it here, and after that we can know what is left child, and also here. So guys, please remember this like approach to put the binary heap into the array. and you can rebuild your binary heap. So here is a, deeper explanation of this problem. So here is a tree, and this one is this array. And next, I would like to talk about the priority queue. Uh, Priority queue is a special kind of the data structure where you can give the priority to the elements, and according to that priority you can build the ordering of the nodes or of the elements. So what is a priority queue? Priority queue is an abstract data type which is like regular queue or state data structure where additionally each element has a priority associated with that. um, so you can build the priority queue, and you can like get access to the elements with the highest priority on a constant time or with a minimal amount of the time. So in a priority queue, an element with a high priority is served before an element with low priority. uh, Priority queue should have the uh, uh, three most important operations. First one, you insert elements, so you put that element into the priority queue, and as you can see, it has two elements inside of the. It has two properties for the insert. First one is the item, so you put the element itself, and of course you give the priority to that element. Then next very important operation is get highest priority. So when you call this function or operation, this operation should return the element with the highest priority. And third one is delete the highest priority. So this operation deletes the element with the highest priority, but it's not also remove the element with the highest priority. It makes that it takes the next element with the highest priority on the place of the previous element with the highest priority. So when you call the delete highest priority, first it removes the element with the highest priority, then it replaces that element with the second element with the highest priority. So whenever you call this function, this function already knows which element. So that's why this get highest priority can spend always a constant amount of the time. Um, Priority queue used in simple array. Um, as I said before, priority queue is an abstract data structure. So you can implement the priority queue with different kind of other data structures. First one is you build the priority queue with just a simple array. So without any ordering. So you insert constant when you insert into the array, which is the priority queue, it takes constant time. So it's amortized. Please take a look on the first lecture. Second, it's a get highest priority. Operation can be implemented by linearly searching the highest priority in array. So and this operation takes off n time complexity. What does it mean? It means that you just take element and put into the array without looking at the as a priority. But the problem is that when you call the get highest priority, you need to go through the all whole elements and take the element with the highest priority. That's why the time complexity takes of n time n. And third one is the delete highest priority. Um, Delete highest priority means that you delete element with highest priority, and because we use just a simple array without any ordering, you need to first find the element with the highest priority, then you need to remove that, and when you remove one element, you need to move all the elements after that element to the left, and that's why the time complexity of the delete highest priority is O of n. So, and the next way is to implement priority queue is to use heaps. So when you use heaps, you use the time complexity, the characteristic of the heaps, of the binary heaps. And if you remember from the previous lecture, the insertion takes off log n time complexity. Get highest priority, please pay attention, takes all one time complexity. So it's in terms of the time complexity, binary heap is more convenient um, for the priority queue, and it takes constant time complexity because um, on the top you have elements on the top of the tree of the binary heap. You have the element which has the highest priority, and you insert element and you delete element according to that priorities, which has the on you like insert and delete on a rules which has a binary heap. That's why the delete highest priority takes log n time complexity, get highest priority takes constant time complexity, and insertion takes also log and logarithmic time complexity. And here is the implementation of the priority queue in the Java. So here you create the priority queue with the type of the string, called this pq, and call this class. And priority queue in Java has three main methods. First one is add. So as you can see, it's a Boolean operator. So whenever you successfully add the element to the priority queue, it returns true. Then second one, you have the pick. So pick means that you get the element with the highest priority, but you don't remove this. And if priority queue doesn't have any elements, it just returns null. And the third one is the size, so it just returns the size of the priority queue. Okay. So in a Python, there is no like specific priority queue data structure, but you can always use binary heap. So for more detailed information about the binary heap in a Python, please follow this link, and um, you can read the documentation about the binary heap. Next, it's a priority queue in C++. In order to declare the priority queue, you write something like priority queue with type of int and the name of this one. And in C++, priority queue has these four main methods. First one is empty. It's actually Boolean operator where it returns true or false. So if it is empty, it returns true. Second one is the size. Function returns the size of the queue. Third one is a push. Push function adds the element as at the end of the queue. And the pop, it just returns the element from the queue. So this is I think that priority queue in C++ is very convenient comparing with Java, because for example, if you see when you want to implement the priority queue, you need to write a lot of the code. Like, but meanwhile in C++ you write the less code, but with the same functionality. So next is problem. So it's called unite sorted arrays. So given k number of sorted arrays, and you need to build one sorted array from them. So As you can see here, there is input. It's a two-dimensional array. It has three one-dimensional arrays, and from this you need to build one-dimensional sorted array. So of course there are many ways to solve this problem. There are many approaches to solve this problem, but try to solve this problem with using maybe the binary heap, or maybe using the priority queue, or whenever you want to use another tree data structure. Okay, so take a pause, think about how to solve this problem, then compare your solution with the solution on the lecture. So here is the approach with using the priority queue. So if you remember, we can build the priority queue, or we can use a binary heap. Uh, we can build the binary heap from this each of the array. So we create one binary heap. Actually, we need min heap. So we put all the elements from the first array into the binary heap, then put these elements, then put these elements, and on the top of our binary heap, we will have the minimum element, which is 0. So we extract 0 and put it on the first place. Then, because we remove the minimum element, the next element becomes the root of the tree, and we take the 1. We remove the 1 from the binary heap and put here on the second place. And on the third step, the next 1 becomes on the top of our binary heap. So we do that step by step till the end, when our binary heap or priority queue doesn't have any elements. So here, whenever, even though that I said it's written here that it is priority queue, it means priority queue with using binary heap, or you just use the binary heap itself. So in order to build the priority queue with and the priority queue is implemented by using the binary heap. The time complexity, think about the time complexity, and also we need to copy all the elements from priority queue into the array. What could be the time complexity? So if you remember, in order to put elements into the priority queue or binary heap, it takes log n time complexity. But let's say that we have n elements in a total, like here. N elements in total, each insertion takes log n, and in a total, the building takes n log n time complexity. Then we copy all the elements from the priority queue into the array. When we extract, it takes the element with a minimum value, it takes constant time complexity, and we need to rebuild that, and that's why the overall time complexity is n log n. Here, copy all the elements from priority queue into array takes also n log n time complexity, because we take from the binary heap the element with the minimum value, and then we need to remove the element from the binary heap, and the deletion takes log n time complexity. And again, we have n elements, and each of the deletion takes log n time complexity, and it's overall n log n time complexity. Next, it's we have unsorted array. Next problem is we have unsorted array, and we need to find the nth largest element. So here's the example. We have 5, 1, 8, and nth largest element is 5. So it's the second largest element. The first largest element here is 8, and the second is 5. Here, same, you need to find the third largest element, which is 3. So the largest one here is 41, then 15, and then 13. So that's why the output is 13. On a third example, we have the duplicate, like the repetition of numbers more than the one. But here you have the largest element is 4, um, second largest is 3, and third largest is 2. That's why its output is 2. Of course, it's again you can take a pause and think about how would you solve this problem and compare your solution. Um, of course, this problem is, I think, it's very easy to solve with the data structure of binary heap. So first solution is you uh, create the array, or maybe you just use the array that is given, and you sort array, and the sorting takes n log n time complexity. Why sorting takes n log n? Because no sorting runs faster than n log n time complexity. That's why by default, when we say it's sorting, we assuming that sorting takes this um, time complexity. And the second is we need to go to the nth place from the nth. It takes also n log n time complexity. Overall time complexity is n log n. This is a first approach to solve this problem. Second is to use, as I said before, max heap or priority queue, which implemented as a as a max heap. So we put every element from array into the priority queue and remove k minus 1 elements from the priority queue. And the time complexity takes n log n again. Why? Because, as I said before, the putting element into the priority queue or max heap takes log n, and we have n elements. That's why in the total, first step takes n log n time complexity. On the second, because we need to remove k minus 1 elements from the priority queue or from the max heap, that every deletion takes log n time complexity, and because we need to remove k elements, the overall time complexity k log n, and the whole time complexity of this solution takes n log n time complexity because we ignore low order term elements. Here is the implementation of the solution in the C++ with the priority queue. So here you have the priority queue, you put into the priority queue, then you remove k minus 1 element, then return element which is on the top of your priority queue. Next problem is very, I think, interesting. It's very tricky problem where you need to find where you need to retrieve the median of the array in a constant time complexity. So what is the median? Median is a middle element in the ordered array. If an array is even size, the median is the average of two middle values. So here's the example. So you have here sorted array, and the median is an element which is only located on a mid of your array. So that's why it's 70. So guys, don't be confused with the average. Average is different. On the second example, you have even number of elements. So you have here 6, and on the middle of your array there are 2 elements, and the median is the average of these 2 elements, so that's why the median is 15. So you in this problem you need to create the data structure which returns the median in a constant time. So, and it should support next functions. First one is insert item, so you add item into the data structure, and second is retrieve the median, so you turn the median in a constant time. So first is you put 5 into some, I don't know, data structure, then you insert 5, and when you call the function retrieve median, it should return 3 because you have two elements and 2 is even, and that's why you need to return 3. Then you add one more element, so in the median becomes 5, then you add 4, then you add 3, and the median becomes 4. Then you add 11, then you add -1. And when you call the median, it returns false. It returns 4. So again, take a moment and think how would you solve this problem, what kind of like tricky things you can create in order to solve this problem. So in order to solve this problem, you use two priority queues. One is a min heap and second one is max heap. So we will divide the numbers into two parts. So first part is the lower numbers and second part is high numbers. First part will be stored in max heap and second part in min heap. So why do we use two priority queues? Why do we use min heap? Why do we use max heap? Because if you took a look on a sorted array, let's take this sorted array, and in this sorted array, if we put everything on the max heap and put these elements into the min heap, on the top of the both binary heaps, we will have the median element. So we put this into the max heap. On the top, we will have 14, right? And if we put everything this one into min heap, on the top of our min heap, we will have 16. So from that, we can say that the median, we just take the top elements from the both sides, and the median would be the 15. So, and if you remember, the taking elements on the top in the max heap and min heap takes constant time complexity. So here is the solution. In this solution, we again, as I said before, we use max and min heap, and when we add elements, we first check the max heap. So by default, we put everything into the max heap, and in the max heap, when the size of the max heap is bigger by 2 than the size of the min heap, it means that we need to take one element from the max heap and put into the min heap. So when we have even number of elements in a total, the size of the max and the size of the min should be equal. But when we have odd number of elements, we can allow that max heap will have one more element than min heap. So every time we check the size of the max heap, and if the size of max heap is bigger by 2 than the min heap, we take element from the max heap, remove it from the max heap and put into the min heap. So we like kind of juggling, so we kind of putting elements, so we are kind of like equalizing the max heap and min heap, and after that the median would be, we can always take the median or in a constant time complexity. So here, as you can see, in the median we first check the size. If the size of max heap and the min heap is equal, we like summing up the values of these elements and divide by 2. If the size of the max heap, it means that if the size of max heap bigger than the min heap, it means that we have odd number of elements, and element which is on the top of our max heap uh, is a median. Okay. Next is we need to find the top k frequent elements from the array. So we have array of elements, and we need to return the top k frequent elements from them. So again, it's a problem similar to the problems that we have solved before. But the problem is that you need to count the repetition of the numbers. So element which has highest number of repetitions has higher priority. So we have this kind of numbers, and we need to return the top k frequent element. So top k, so two most repeated numbers. So here you see that 6 repeats two times. 3 also repeats two times, as you can see, and all other elements repeats only once. So 3 and 6 they repeats most of the time. So it's a top k frequent element. So what do we do here? Again, take a pause, think about how would you solve this problem. So in this problem, we use one more additional data structure, hash map, where the k is the element itself and the value is the number of repetition. In order to build the hash map, it takes all of n time complexity. We just go through the array, and whenever we have meet the element, we add one more into the value, and it takes all of n time complexity. And after that, hash map helps us to know how many times each element repeats, but we don't know which one is the most repeated, which one is most frequent element. In order to know that, we build the priority queue according to its frequency. So we put every element into the priority queue according to its repetition. So adding element into the priority queue takes log n time complexity, and we need to do n times, and as a result, the building the priority queue from the hash map takes log n time complexity. Then we need to collect like k elements from the top of our priority queue, and it also takes k log n time complexity. So if you remember, again, the removing the element from the priority queue which built on the top of the binary heap takes log n, and we repeat it k times. So overall time complexity is n log n. Here is the solution. And the next problem is you need to design a dictionary of words. So design a data structure that supports the following functions. So you add some words into some kind of dictionary, and then when you call the operator search and you write some word, it should check do you have that word or not. So here in this example, you add words, add, then you add ads, then you add QWERTY, then when you search QWERTY, it returns true. Then, for example, when you write like search a dot dot, it means that after a it can be any letter. Because we have ads, it returns true. Then we search like dot dot s, it means that there is like any letter between any two letters between s, it also returns true because we have this ads. And on next, when we search dot w, it return false because we don't have any words which consist of the three words, and before the w there is like two letters. That's why it's false. Okay, so in order to solve this problem, we use a tree where each node is one letter and the children is the next letter in the word. So how would it look like? So first, in the first operation, when we have add word add, we like build the uh, like subtree as like this, where we have some empty space as a root, and we say that the child of this is a, then the next child of the a is a d, and then again d. So by the way, please don't be confused with a binary tree. It's just a tree where each node can have many like many children, more than the two. Then we have the adds. Uh, on the adds, you don't build one more branch. You just add one more children to the add. So um, you don't need to like do create one more branch with one more a was one more d, because here you have already these nodes and in this ordering the only difference is the s. That's why you add s as a child to the d. And the next it's QWERTY. In the QWERTY you because we don't have the word which start with a q. By the way, here I missed e. Okay, so sorry, here I missed e. Yeah. So we build one more new branch where it starts from q and ends with a y. So whenever we do the search, we first start with a q, so we start from the root, and we go to the next node. We see like, is there any node, is there any children of this empty space which starts with a q? Yes, we see. Then we check this letter. Does this q has a child with a value of w? Yes, it has. Then we go to the e, then goes y, and if after y we don't have anything, it means that we are finished with that word, and it's just why it's returned true. On the next, it's a. Um, Here on a, we start with this letter. Then we take then we check, does A has any children? Yes, it has. So we go to the D. After D, does D has any children? Yes, it has two child. So two children. That's why we return the true. And same applies for this search, and same rule applies for this search. And actually, this kind of tree is a special data structure called the tries. That a trie is a variant of an tree where each character are sorted at each node. In each pass down, the tree may represent a word. The advantages of the tree is that we can insert and find strings in O of L time complexity, where L represents the length of a single word. And this is faster than the binary search tree. And it's also faster than hashing because it's way of the implementation. We don't need to compute any hash function. We can do like this kind of operations when we don't know like the whole word, uh, but we know the length and it from which letter does it start. So for these cases, for this kind of searches, the try the, the try is very convenient. And also another advantage of the try is that we can easily print all words in alphabetical order, which is not possible with hashing. Also, we can do like prefix search with a try. So prefix search, as I said, we can just like type one word. Let's say that we are searching one for the word on the life, and we start with a letter like A, and we with the data structure of try we can have some kind of option of which word do we need to use, and it's very popular with the autocomplete softwares. So here is a example, like graphical example. The only difference that after the some word we have like sign. Star sign means that there is one word which uh, starts with a M, then goes N, then goes N. After N, we have the star method, and we are done with that. So that's it. Um, tries are quite like uh, omnipresent data structure. It means that I guess most of you have already used try even without knowing that try exists. For example, in a Google search, when you type some word, it offers you some kind of variations. So, and next, maybe you write something on a T9, and T9 helps to choose which tries to predict which word do you want to use. And next, it's on a, like spelling. Uh, on the spelling, for example, you choose one word, and like if you skipped one letter, with help of the try, the software can like predict or can like fix your error with using of try. So tries are like I think one of the most used data structure in the software, and a lot of people used try without even knowing that it's a try behind the scenes. So today's summary of the lecture is that there is a special queue called priority queue where you can give the priority to the elements. So this priority key is one of the most important data structure, one of the most convenient data structures for problem where you need to work a lot with the mean value, with the max value, or with elements which um, where the priority of that element is not related to the value, but maybe some other additional characteristics. So try to implement the priority queue and try to solve the problems on the priority queue. So that's it for today. Thank you very much, guys. See you.